this video, we'll cover section 7.3, which is volume using the shell method. In section 7.2, we talked about the disc and washer method by revolving a figure around an axis of revolution, which would be adding up a bunch of circles or washers. But now with the shell method, we're going to be adding up a bunch of shells, or really what we are, the outer shell of a cylinder is what we'll be adding up. Just to kind of see where we're coming from, I'm going to not do this outer radius, inner radius thing, and I'm going to change my diagram a little bit. We're not going to worry so much about these over here, and we're going to call P R, because I like R better because it represents a radius. All right, so what I like to do is simplify it down a little bit. So we have this shell, or in other words, I like to think of it as like a toilet paper roll. So that's really what we're looking at here. With this toilet paper roll, or this shell, we have this height of that cylinder, and then we have the radius of that cylinder, which is this distance from the center to the outer length. Now, if you look here, we have this little bitty W, which represents that I do have some kind of width to that, but ideally what we're going to end up doing is that width is going to become infinitesimally small, just like we've seen on other things. So if I were to find the volume of this shell, we would be looking really at the lateral surface area of a cylinder. And so that lateral surface area is obviously an area, not a volume. And so in order to get that volume, we would then multiply by some width, and then we would have the volume. All right, so we need to find that lateral surface area because we don't have the top or the bottom. Those have been cut out. So the surface area of a cylinder is just simply the circumference, right? So that outer circle, and then times that height. So the circumference of a circle is 2 pi r times the height, and then times some width in order to get that volume. So then if I add up a bunch of those and make the width infinitesimally small, we have that integral representation. So we have 2 pi times the integral. Now r and h are now two separate functions, and that's new now. And then the width becomes infinitesimally small, so that's our dw. So we'll either have dx or dy. All right, so with the disc and washer method, we were trying to find what the r's were. And now for the shell method, we're finding two different things, both in r and in h. So we have the horizontal axis of revolution and the vertical axis of revolution. Now what makes this different, how you can tell when you're going to do shell versus disc or washer, is with disc or washer, our representative rectangle was perpendicular to the axis of revolution. But now with shell method, if you look, here's my axis of revolution, and then my representative rectangle is parallel. All right, so if those are parallel, then we're using the shell method. So again, if you want to write that down, you can write down axis of revolution is parallel to the representative rectangle. So that means you're going to use the shell method. Now, also on here, I'm going to change the P's in the diagram to R's. Okay, so now we have those two functions. We have the R and we have the H. So off here to the side, I want you to write down what those represent. If you look here, the H is, in both of these diagrams, is the length of the representative rectangle. So you could say the length or the height of the representative rectangle. Okay, so that's going to be the H. And then the R, if you look, is going to be the distance from, if you look at both of these diagrams, the R is starting from the axis of revolution and then going out to that representative rectangle. So the R is the distance from axis of revolution to the representative rectangle. All right, so that's very important to remember for shell method because a lot of people get those confused. And so you have to have both of those for shell method, whereas disc and washer, you only had one thing. Okay, now down here in the bottom, I have a little bit of a diagram to help you visualize. However, of course, the printing was really, really bad, so you can't really see what's going on here. I brought up some things which are not on your notes, but I just want you to see it here. So here's kind of a better picture of the shell method. So we have this region R here, and we revolve it around the y-axis. So this would be taking vertical cross sections. So like this. And then when you rotate that around, you'll get this cylinder here. Okay, so you can kind of see that there. And even better, if you look at this example, it's like I took those cylinders, so of different widths, and I kind of sliced into it. So you can see this is my representative rectangle, and then that's been rotated around that axis of revolution. Okay, so that's kind of a piece inside that. So I want you to see the difference between what the shell method looks like versus the Disker washer method. All right, so let's try some examples. So just like in the last section, I just want to set up my integrals. I'm not going to actually solve them, so we're just going to get an expression. So for this one, we're going to revolve x minus x cubed and bounded by the x-axis from 0 to 1, and then we're going to revolve it around the y-axis. All right, so since we're revolving around the y-axis, and this is on shell method, the y-axis is vertical, so that means we want vertical rectangles. So that means we're going to take with respect to x. Okay. So we're going to graph this really quickly. So I'm just going to graph these. If you don't know how to graph any of these, I'm okay with you putting in the calculator. But you're going to get a function that looks like this, and then that's going to be rotated around the y-axis. So I'm going to draw my representative rectangle here. And if you want to draw your rotation, you can. So I'll just kind of show you. It'll look something like this. And then when I rotate that, I'm going to see if I can draw my cylinder. It would look something like that. Okay, so there's my cylinder. All right, so within that cylinder, I want to find the height and the radius. So the height is just this bar here. And then the radius starts from the axis of symmetry or axis of revolution all the way out to that representative rectangle. So that's R. Okay, so I know that gets pretty complicated, especially if you don't have different colors. All right, so we need to define H and R. So H is the representative rectangle, so that's vertical. So we're going to take top minus bottom. So that's just x minus x cubed. Then the R, this is where it's a little bit weird at first, but R's are actually really, really easy. The radius. This is a horizontal length, so we're going to take right minus left. So what the right is determined by is the representative rectangle. So what is that x value, essentially? We don't know. So it could be because our representative rectangle could have been here, could have been way out here. All we know is it's bounded by some x value, and it's the same x value all the way down because it's always going to hit that representative rectangle. So our radius is just going to be x, and then minus the right, which is, the left, which is just the x revolution here, which is 0. Okay, so typically your radius is just going to be an x value or a y value, especially if your x revolution is the x-axis or y-axis. All right, so now if we put this together into our volume formula, remember from the front, we're adding up a bunch of shells. So instead of just pi, we have 2 pi in front. So this is going to be 2 pi times the integral from, if you look at just the one region from here to here, that is going to be from, I believe, 0 to 1 of the R times the H. And that is my answer. So of course I could simplify that, but I'm not worried with that for today. Okay, so again, you want to find R and H. And that's probably the hardest part for this. So let's keep trying some examples. So number 2, find the volume of a solid of revolution formed by revolving the region bounded by the graph, x equals e to the negative y squared. I know that's a really ugly graph, but I'm going to give you the graph, so it's okay. All right, so the graph of this is going to look kind of like, and it says it's bounded from 0 to 1 on the y-axis, and actually be bounded by 0 to 1 on the x-axis, the way the graph works out as well. So to graph this, it's going to look some kind of like curve like that. It keeps on going up, but we're going to cut it off at 1. So this is my region here that I'm going to be rotating. Now, since I'm rotating about the y-axis, the x-axis, that is a horizontal axis of revolution, so we're going to take horizontal cross-sections, which means we are going to take with respect to y. All right, and you can see our equation's already in terms of y, so that works out. So now we need to figure out R and H. So again, H is just the length of the representative rectangle. So since that's horizontal, we're going to say that's right minus left. So the right function is e to the negative y squared minus 0. And then the radius is going to be from the axis of revolution, which is the x-axis, up to that representative rectangle. So top minus bottom. So that top is just some y value minus 0. Okay? Bring that together, and we get 2 pi times the integral. Since this is with respect to y, we want to use the y value, so 0 to 1. Wouldn't matter anyway, but that's okay. And then the radius, y, times the height, e to the negative y squared. And that is my answer. All right, so down here we just kind of have a summary and a comparison of the disk and shell methods. So this is something that's a good reference guide. So it tells you how, if you have vertical axis of revolution, what formula to use, and also with how to take your integral with respect to. Okay, so each of those gives you the different formulas based on the axis of revolution and the orientation of the graph. So that's just for your reference. Okay, so for number 3, find the volume of the solid formed by revolving the region, x squared plus 1, x and y-axis, and x equals 1 about the y-axis. And if you actually can remember, we did this graph on the disk and washer day. So when I graph this, it'll look like this guy. And so when I rotate that around the y-axis, you will get a shape that looks kind of like that. All right. So what we did, if you'll recall, you can look back in your notes for 7.2b, I think it was example 4, we split this into 2, and we found the top and the bottom because we were doing the disk method. But now we can actually do this all in one with the shell method. So with the shell method, you're taking parallel cross sections, or representative rectangles, I mean. So that means we don't have to split it at all. It's just that one method. So actually, in some cases, shell will be easier than disk or washer. All right, so that is with respect to x. So let's find our h, which is going to just be x squared plus 1, and our radius, which is just bounded by some x. So then the volume is 2 pi times the integral from x value, 0 to 1, of x times x squared plus 1. Okay, so instead of having to split that into 2 integrals, I could have just done it with 1 with the shell method. And if you evaluate that, you'll get the same answer. All right, so our final example is a little bit more challenging. So we have the function x cubed plus x plus 1, bounded by the lines y equals 1, x equals 1, and then rotated around the line x equals 2. So again, I'm just going to give you the graph to you. So it's going to look like it's bounded by y equals 1 and x equals 1, and it'll just kind of look like this. Okay. All right, and then that's bounded by the line x equals 2. Or sorry, rotated around the line x equals 2. So that is vertical. So our rectangles will be vertical. So now I have this huge gap with the shell method. So this is where our radius is going to change. So our height also is going to change here because that height now is not bounded by an axis like it was in all the other examples. So our height is really bounded by 2 functions. The top being x cubed plus x plus 1, and then minus the bottom just being the line y equals 1. And then the radius, if you look, so that's our height. And then the radius, I'm actually going to draw this one out, starts from the axis of revolution all the way out to the representative rectangle. So remember, we talked about that representative rectangle being some x value. But now we have the right minus the left. So the right value is actually 2. So that distance would be 2 minus whatever x value you're at that moment. Okay, so that is where it can change on you. All right, so our volume then would be 2 pi times the integral from 0 to 1, and then our r is 2 minus x, and our x is going to end up being x cubed plus x, because these two ones will cancel, and then dx. The problem then asks us to find the volume of the same region revolved around the line y equals 3. So here I've redrawn this. Now, we've been learning about shell method. So if I was to do shell method, you would do horizontal cross-sections here. However, in order to do that, you would have to put things in terms of y. And if you look back up at our equation here, that's actually not solvable for x. You can't solve that for x and put that in terms of y. So this is one where you can't use the shell method. So this is an example of where you would be forced to use one method over the other because you couldn't get it in terms of x or y. All right, so this one, we're actually just going to do a repeat of the disk method. So let's kind of write us a note there. So disk, or washer, that is, instead of shell, because impossible to put in terms of y. Okay, so just a little note there. So let's just review disk or washer. So if you look at this one, so we don't want to do the axis, we don't want to do horizontal cross sections, we're going to do vertical cross sections. Because remember, disk or washer, you do perpendicular cross sections to the axis of revolution. All right, so now this is going to be washer because you're going to have a huge gap. So remember, with washer, we need to have our two radiuses, or radii. So we're going to start with the big R, starts here at the axis of revolution, goes all the way to the outer function. So big R is the top function, which is that cubic, x cubed plus x plus 1, and then minus our bottom function, which is -3. So you're actually going to be adding that 3 on, so that's going to be x cubed plus x plus 4. And then the smaller radius, again, from the axis of revolution up to that bottom line, and that's just going to be top minus bottom, so that's going to end up being a radius of 4. Okay. All right, so then to write that equation, remember the disk and washer method are adding up a bunch of circles. So not the 2 pi r, but pi r squared. So that's going to be the integral from 0 to 1 of big R squared minus little r squared. And then dx. Okay? So, actually, in the AP test, shell method is not used quite as much. It's really disk and washer, but that's something that I think is valuable to see.